So anyways, we're going to be considering this next claim here. And so to make this proof work, I'm going to assume that you are convinced sufficiently that log base 2 of x is less than x for all x that are positive real numbers. So I'm going to presume that this is in fact something that you're familiar with. Like, this is a true statement, but I'm just going to take this as a given. So I want to show you how you can use this claim akin to how we prove that log base 2 of n is big O of n. I would like to be able to show you something that's a little stronger of a claim. So here's the claim. That m is looking a little bit melted. For any real constant, epsilon, which is going to be greater than 0, it has to be that log base 2 of n is big O of n to the power of epsilon. So this means things like square root of 2, we're talking about like n squared, all of them. So every polynomial that's in here, like it means that the logarithmic function does not, if you want to put this in growth rate terms, it's saying that any logarithmic function will be eventually dominated by some polynomial of any exponent that is greater than 0. That's the claim. So this is one way you can justify to somebody that, oh, if you have an algorithm that runs in logarithmic time versus one that runs in polynomial time, well, if the exponent is not terribly big, but it's big enough that it might make a difference between choosing between a logarithmic one and say square root, like I say if it was log base 2 of n versus square root of n, you can use this to show that square root of n would be in fact something that would bound it eventually for a sufficient constant and sufficient value of n. So let's prove the claim. It's going to be rather nice and slick for us. So as per usual, we need to come up with a game plan here. To prove the claim, we compute constants. C, which is a positive real number, and n0, which is a positive integer, so that for all n greater or equal to n0, log base 2 of n is less than or equal to c times n to the power of epsilon. So what I'm going to do is, remember, epsilon is a constant, so I'm going to use it. So what I'm going to do is I'm going to try to make something that looks a little bit like the left-hand side, but I need to do a little bit more to make this work. So what I'm going to do is I'm going to pick the constant for you, and I'm hoping that you'll stick around with me for the ride. So I'm going to pick c is equal to 1 over epsilon. Then we find n0 so that log base 2 of n is less than or equal to 1 over epsilon times n to the epsilon for all n greater or equal to n0. Okay. So if I can make something that reminds you of this statement up here, then we're done. So if I can make something that works a lot like that, then we're done. So you'll notice that you might look at this and say, Dan, is that a positive real constant? Well, let's think about it. If it's, say, some fractional number, like say if it's like 1 over pi or something, well, that's going to be some number that is less than 1, but most certainly it just makes this larger, right? 1 over something less than 1 will most certainly make this larger than 1. If it is, say, 1 or greater, then it's just going to be 1, or it's going to be, if it's greater than 1, then this is going to start being something that is going to be less than 1, but it's going to still be positive. So now we're going to use the power rule of logarithms in a following very cheeky kind of way. So watch this very carefully. So I'm going to manifest an exponent using properties of exponents. So watch this carefully. This is a little slick trick I'm going to pull on you. Notice by invoking the power rule of logarithms that we can rewrite log base 2 of n as follows. Log base 2 of n to the power of epsilon raised to the power of 1 over epsilon, right? Because remember, this will have it where it turns into a product, right? Epsilon times 1 over epsilon is just 1. But what's this? This is just simply 1 over epsilon times log base 2 of n to the power of epsilon. Interesting, right? That's interesting. So you're staring at this and you're like, okay, so what do you do? So what do you do with this? Okay. Well, let's go over to the other board here. Let's think about this. And you're going to see that when we have two things that we know are one is less than or equal to the other, that if I apply it to equally, like apply an operation to both of them equally, meaning that, say for example, like we take logs of both sides or we exponentiate both sides as we're going to do here, that I should be able to maintain the same properties given the fact that exponentiation, if one thing is less than or equal to the other thing, then since it's an increasing function still, when I exponentiate, then it still has to be, if this is less than or equal to that, then the result of that has to be less than or equal. So now I'm going to use this fact that we have over here. Since log base 2 of x is less than x for all positive reals, then it has to be, by simple extension, then log base 2 of n to the epsilon is less than n to the epsilon for all n greater or equal to 1. Does everybody see what I did here? So remember, this is just the input of the logarithmic function. This is the input for what x would be. So you just put I'm just putting the same quantities into here. So because this is true, this has to follow, right? Because these are the same, like this is like, if you imagine x being n to the epsilon in both these cases, remember, epsilon is a constant, right? It's just taking whatever that number is and applying something, which will end up still being a positive real number, right? Because this is the much more general statement. So I'm just going to use it. And thus, so now we have this, and thus, for all n greater or equal to 1, we're going to now bridge it. Log base 2 of n is equal to 1 over epsilon times log base 2 of n to the power of epsilon, which we've established that this is less than or equal to 1 over epsilon times 1 over n to the epsilon, right? Because it's just 1 over epsilon there, and I'm just going to tack that on. Just going to hitch it for the ride. So now, I know this is true for all n is greater or equal to 1, so I'm just going to select n0 is equal to 1. Therefore, for all epsilon greater than 0, by the definition of big O, log base 2 of n is big O of n to the epsilon. So for you in plain language, this is saying that any logarithmic function of this sort is always going to be dominated eventually by any one polynomial of that form, n to the epsilon. So all of these belong to n to the epsilon regardless of what epsilon is. So for example, you get as a consequence of this, So a consequence, as an example, is that log base 2 of n is big O of square root of n. So if you have an algorithm that runs in square root of n, you know, if I gave you two algorithms, one where one runs in big O of log n, the other one runs in big O of square root of n, this is telling you right up that that logarithmic function is going to be potentially faster than the square root of n. So for sufficiently large n. These are both, by the way, pretty slow moving, but most certainly the logarithm will grow much slower. But yeah, no, so isn't that pretty nice? So using a very basic property that you could derive, say, in a calculus class, you most certainly can come up with something quite slick like this.